So we're just going to start with some relations. Well, relations is really just an input and an output. A more mathematical way is it's a set of ordered pair. A set of ordered, that has an E in it. Ordered pairs, or pair, it can even be one pair, but we'll go with pairs. So an example of that, we could just do, I don't know if I want to just do this. Yeah, why not? An example of this might be, we'll have the ordered pairs 5, -3. We could have a 6, 2. We could have, I didn't know people hated a 6, 2. 7, 0. That's enough. 3 of them are good. That is a relation. That 5 goes to -3, 6 goes to 2, 7 goes to 0. We can make a table of that information. We can make a table that we can say one thing's an input and one thing's the output, how they map to each other. So if we look at these first terms, we usually call those our x values or our inputs. So if I was doing a table of this, I'd probably put 5, 6, and 7 right in my table for my inputs. Well, when I see 5, that pairs off with the -3. The 6 went to the 2. The 7 went to the 0. Mapping is a whole lot like making a table, except we actually draw arrows of the direction things work. So with mapping, I need that 5, 6, 7 in one of these oval shapes, 5, 6, 7, and I need all of those other numbers over here. I'm actually going to put them in numeric order, -3, 0, and 2. Typically when you're mapping, you put them from lowest to highest in value. Now when you're mapping them, it doesn't say that 5 goes to -3, 6 goes to 0, 7 goes to 2. You have to draw arrows to say where things map to. So according to this table over here, it said 5 went to -3. It says that 6 goes to 2 and 7 goes to 0. So when you're mapping things, the arrows are what tell you what things pair off with, not the order in which you list them. Now a graph of this might be 5, -3. Well, I don't have that on there, so let's just pick new values. Let's just pick kind of a normal graph that we'd have a 1, 1, a 2, 4, and we could have a graph that looks like that, half a parabola. Or more traditionally, we put things as equations, considering we just did that. The equation I picked, doesn't matter what equation you pick, y equals -3x squared plus 7. Now the difference between my table, mapping, graph, and equations. If you look at my table and mapping, I have 3 things, 3 items in there. This graph has an infinite number of items in there. So does an equation. Has an infinite number of things I can plug in and get out. So you think you could plug in 1, 2, 3, 4, 5, 6, 7, 8, 9. You could also plug in 1.01. You could plug in 1.00000000001. So these are kind of an infinite set. They're still a relation. They just have an infinite set, where these are usually finite examples of a relation. All right, yeah?
Can you explain the graph again really quick? I'm confused on that.
I just made up a graph.
Okay.
Yeah, I didn't pick any values that related to these. I just picked a half a parabola. I picked 0, 0, 1, 1. But you could draw a straight line on here. It's just an example of a graph you might see in a class.
So it doesn't matter?
Doesn't matter what graph you draw.
Okay.
Yeah.
Wait, so how do you know what the equation is?
I just made up an equation.
Oh, okay.
I just said this is an example of an equation. Another example of an equation could be y equals 2x. Another example of an equation could be y equals x plus 3, take the square root of it.
Okay.
All right, just an example of when I say equation, that's what I'm talking about. When I say graph something, you should graph something. When I say put it as a mapping, we'll put it as a mapping. So those are all just arbitrary things. All right, now let's talk about, I've already talked about these terms, inputs and outputs, but a more specific term is a domain and a range. Our domain are going to be our inputs, and our range are going to be what we get out when we put a number in. So these will be our outputs. That's realistically what they are, but for most of the time, now this is not hard, fast, always happens, but for this class, for like algebra, most of the time when I say inputs, you're going to think x values. When I say outputs, you'll most likely think y values. That is how your graphs are set up. That's how your calculator is set up. That is generally how we deal with these things. That when we set up an equation, our x values are input and our y values are our output. We could definitely change that. I could have rewritten these as being x equals negative 3y squared plus 7. That would make y my input and x my output. We traditionally don't. Traditionally, x is our input and y is our output. So when I talk about domain, we're thinking about what are my x values, outputs, what are my y values. So we're supposed to give the domain and range of each of these relations. When it's a set of points, it's pretty easy. You just got to figure out which one of those means your inputs and which one means your outputs. Your inputs, if I give you points, are always going to be that first number that's there. So when I'm looking at my inputs there, I'm looking at -1, I'm looking at the 7, I'm looking at the 3, I'm looking at the -5. Now, traditionally, you put them in numeric order. So my smallest one there was -5, I said. So once again, I'm picturing these x values here. So I have 4 to choose from. -5 looks like the smallest one. Then it looks like I have a -1, then I have a 3, and then I have a 7. Notice I did not use parentheses, I used braces. Braces indicate that you're using each value and that's it. Parentheses mean you're using all the values in between them. So if I had parentheses here and here, I'd say use all the numbers from -5 to -1, use all the numbers from -1 to 3, 3 to 7, which is not what I want. I want those 4 individual elements. So braces mean individual element. All right, our range is going to be what we get out. I'm going to circle my ranges. My ranges include that -1, that 4, that 0, and that -1. Now, notice -1 repeats itself. I am not going to repeat it. I'm going to write -1 once. It just happens twice. But my range still just includes a -1, it includes a 0, and it includes a 4. So when you're making these lists, do not repeat numbers. All right, for our next one, and I want to get into these notes a little bit. If I don't write any numbers on there, it means the scale is 1. If you write a graph, you are not allowed to do that. I'm allowed to cheat. So if you don't see numbers on there, that means the scale is 1. So if I was listing all of these points, we'd go back 1, 2, 3, down 1, 2, 3, 4. So it might be a good idea to name these points. This point right here would be -3. -4. I'm just going to I'm going to loop around. So I'd go a +1, -3 for this next one. 1, -3. For the other one, my x would be 2. My output would be 0. For my next one, I'd have 1, 2. And for that final one, I would have a -1, +1, 2, 3, 4, 5. So remember, our x values are our inputs, our y values are our outputs. Now, the nice thing about having a graph, if I want to list my domain from smallest to largest, I'm going to go to the one that's furthest to the left and work my way right. So that will start with a -3. It will then be a -1, a +1. I'm sorry, I missed one. No, yep, both those are 1, and then a 2. So my domain is going to... Brace, yes. Yep. Yeah, perfect. That's a good way to look at it because it's a dot, it's not a line. So we have -3, we'll have a -1, we'll have a 1, and we'll have a 2. For range, we're going to go from the lowest value to the highest value. So range are y values, so lowest to highest. Get in the habit of thinking of this way. Lowest to highest, my lowest point is at that -4. Working our way up. Yeah, go.
How come it's not like -3 through negative or through 2 and including all this because the line touches all those values?
Is there a line on there right now?
No.
No. So we don't include, these are just points.
Oh.
I'm allowed to just put points on there. Now, just like on the test, some of us made assumptions that we had to solve for stuff. Like I would say just factor it and all of a sudden you'd solve it. Don't put more work on there than I put on there. I just put points. I never said connect the dots. So these are individual points. Our lowest one was -4, -3, a 0. Looks like we have a 2, and it looks like we have a 5. These are the easiest ones when it's in this form because they're already organized for you. Our domain is going to be a -2, -1, 0, 1, 2. And my range is just going to be 0, 1, and 4. Now, I stressed using braces on these, right? That's because on the next one, this is where we're going to get to what you talked about, Grant, that we're going to include a bunch of points. Notice all these aren't points anymore. These are straight lines. I need to include every input and every output that could possibly be on this line. Now, the way I look at domain and range, when I see the word domain, the first thing I think of is x values. Look at where your x-axis is. It's right here. My x-axis runs from left to right. When I ask for a domain, I'm asking you how far left does the graph go to how far right does that graph go, because it's all the points in between. It's going to be -infinity to positive infinity. Bless you. If I put my finger on this, now as I walk, I'm walking left and right. I know my finger's going down, but I'm walking all the way left. This will continue forever going in that direction. So when I'm looking at domain, once again, I'm looking at my domain runs all the way from that direction, all the way to that direction, and we're not missing any points. There's another way I would teach it in like an Algebra 1 or Algebra 2, is when I look at this, and it's hard to picture sometimes for some people, if I squish this onto the x-axis, it would make a straight line going in both directions. If I squished all of these points up, these would have to curl up and be flat on that x-axis going on forever. So our domain needs to be from between, so now I have to use a parenthesis. -infinity to infinity. Now remember, we might have to use brackets or parentheses. Those are our two choices. We use parentheses when we don't get to that number. We will never get to infinity or -infinity. If you did, you'd be a rock star if you could count to infinity or -infinity. Don't try it. You'll be doing it for infinity. But that's why we use the parentheses here. All right, range, on the other hand, is how low does the graph go to how high does the graph go. If I traced my finger all the way down and kept going with this graph, how low would my finger go? It would go -infinity. So when I'm talking about range, I'm saying this graph goes forever down. So that's going to be -infinity. Can I keep this finger going up and up and up and up? No, so we know there's some stop point.
6.
So that's where we find our highest value. And yes, 6 is perfect because we have to use our y values to describe how high it is. This is like the one time you use a y value to describe where something ends. So our highest point is right here at 6. 1, 2, 3, 4, 5, 6. So our range starts here, and it will be a closed dot unless otherwise notified. That'll be our range, and it goes all the way to 6 right here.
Do we have to draw that?
You do not. I just find students that struggle with domain and range, this can really help them realize which one goes where. Now, we're going to say it goes to 6 and includes 6. So I'm going to put a bracket on it. The way it's not going to include it is if I put like asymptotes on it, or I put a circle saying it does not include, so an open dot. So this one has a closed dot. So that means we're going to use brackets. How far left does this graph go? It goes to 1, 2, 3. It goes -3. How far right does this graph go? It goes infinity. So my domain looks like this. I can input any number from -3 forever, and it will touch the graph. So this goes from -3 to infinity. Let's put that down with a bracket. I'm going to go back to black. -3 to infinity. Does our graph go forever down? No, our lowest point is right here, right? And it looks like it's at 1, 2, 3, 4, which is -4. So our range starts at -4. I'll go ahead and put that over here. Our range starts at -4. That's our lowest point. And it's going to keep going up and up and up and up forever. So our range will start at -4, but it will continue to go up forever. So it'll be -4 to infinity. I will never grade you on those domain and range bars, but I promise you, if you struggle with domain and range, those can really, really help you understand it with the graphs. Now, when I give you an equation, I ask for the domain and range. That's where you have to really think about what domain and range are. In fact, when I ask for a domain and range of a function, I'm asking you, where's this function broken? And what I mean by that is, if I look at this, I'm looking at square root. Is there a number you can't take the square root of and get a real number out? I could take the square root of 0, because square root of 0 is 0. So that's fine. I can't get any negative numbers. I cannot have this being negative. We can't take the square root of a negative. So what does that mean to us? That means that this right here, that x plus 1 can't be negative. And it can be 0 though, right? It can be 0. So what I'm looking at is, well, x plus 1, a mathematical way of saying this can't be negative is x plus 1 must be bigger than or equal to 0. It's okay if it's equal to 0, it just can't be bigger, or it can't be less than 0. If I solve that, x needs to be bigger than or equal to a -1. I can plug a -1 in there and I get out 0 and I'm good. I can't plug a -2 in because -2 plus 1 would be a -1. Can't take a square root of -1. So I'm looking at what will make this 0, and anything bigger than that will work. What can make it 0 and anything bigger will make it work. So our domain, our lowest value we can plug in is -1 to infinity, because I can take the square root of a really, really, really big number. All right, if I can't plug negative numbers in, there's a chance I can't get negative numbers out. Do we see a plus and minus on here up front? Do we put that anytime we see a square root? No. People on tests, no. There is no plus or minus here. And if I can't take a square root of negative, there's no way to get a negative answer out. So then we have to think about, what's the smallest number I can plug into this? I can plug in -1, and what's the square root of 0? 0. I could plug in really big numbers, right? But I can't plug in anything smaller than what would get out a 0. So our range is actually going to be, I only can get out a 0. That's the smallest. The smallest thing I can plug in is -1, I can get out a 0. I can plug in bigger stuff. I can plug in 2, 3, 4, 5. And the bigger number I plug in, the bigger my output's going to be. So my output's going to be from 0 to infinity as well. And if you know what a square root graph looks like, it looks like this. This is not the one that matches this. X plus 1, we would actually be down here, and we'd go up like that. All right, questions on domain and range. You need to know how to do it from sets, from graphs, and from simple equations. All right, let's build to the bigger thing. Functions. Functions. A function is a special type of relation. So we can have a relation that's not a function. A function is a special type of relation in which each element of the domain is paired with exactly, let's not put exactly, let's put only. Only one element of the range. The domain is paired with only one element of the range. So every input can only have one specific output. 2 goes to 3, 3 goes to 4, 5 goes to 6. Each one has to have a unique output. So when you're checking to see if things are a function, you're looking at each element of your domain and making sure it just goes to one y value. Each x value can only go to one y value. So when I'm asking you determine whether a relation is a function, you're going to make sure -3 just goes to one number in -4. That works. -1 goes to -2, 2 goes to 1, 5 goes to 4. This is a function. I don't have any numbers in my domain that go to 2 elements of our range. So yes, this works. That's a function. For number 8, my one goal is to make sure every element of the domain goes to only one element of the range. How many numbers does -9 map to? It goes to -2, it goes to 5. This is not a function. It is not a function because -9 goes to 2 different range items. This is a big old no. Okay, my next one, we have -7 going to 2. We got -5 going to 2.
It's still a function.
Why is it still a function?
It's 2. It's 1y going to 2 x's.
Oh, did I say anything about every y has to go to 1x, or did I say every x has to go to 1y? Every x has to go to 1y. Does -7 go anywhere else besides 2? Does -5 go anywhere besides 2?
No.
Does -2 go anywhere besides 8? Does 0 go anywhere besides 8? This is a function. This is a function. The only time you're worried about not being a function is if you have 2x or 1x value going to 2y values, not the other direction. So, yep, this is a function. This works. Are we all clear on that? Because that can be really confusing.
Say that one more time. 1y, go 2 x's?
1y can go to 2x's. Kind of like, see that both these 2 goes to a -5, and that's okay. When I teach this in like an Algebra 2 class, and if this isn't clear to you, I always taught this as a mailman function. Picture your inputs as an envelope being delivered in a mail. And your mailman is a function. Each letter goes to one mailbox, right? So each mailbox goes to one number. So envelope -3 goes to mailbox -4. -1 goes to -2, 2 goes to 1, 5 goes to 4. However, if a mailman has a letter -9, is it okay if your mailman tears it and puts it in 2 different mailboxes?
Yes.
It is not okay. In fact, it's a felony. So this is a felony. It's not a function. This is one envelope going to 2 mailboxes. Is it okay if I have letter -7 and letter -5 and he puts 2 envelopes in the same mailbox?
No, that's a felony.
Yes, no, that's not a bad
You silly goose.
So picture your domain as envelopes. If you have to tear it apart and put it in 2 mailboxes, that's a no-no. You can put more than one piece of mail into a mailbox. That's what's happening at number 9, but you can never tear it apart and put it into 2 mailboxes. So that's how functions work. An easy way to tell if something's a function is to graph it and do something called the vertical line test. The vertical line test is testing how many elements the domain goes to, or how many outputs the domain goes to. Now, if a vertical line intercepts relation at more than 1 point, so if it hits more than 1 point, then the relation is not a function. So your job is to picture a graph and then picture a vertical line, just passing over it. And you're making sure that vertical line never hits more than 1 point. So if you look at this graph, there is no place that this will hit more than 1 point at once, which means this is, in fact, a function. This is basically saying -1 maps to 0. That envelope goes to one place. This envelope goes to one place. This envelope goes to one place. However, if we look at number 11, there's a lot of places where I can put a vertical line where it fails the vertical line test. That fails, so it's not a function. Once again, this is one envelope going to 2 mailboxes. Right, Chris? Got all that? All right. For the last one, those can be a little confusing, especially when we have like vertical asymptotes and stuff. It actually passes the vertical line test. At no point does this actually get straight up vertical where it fail. Just like this, at no point does it get straight vertical where it won't pass that vertical line test. This is a function. In fact, it's a very specific type of function. Those are those rational functions like 1 over x that were so fun to deal with. But that definitely passes the vertical line test. All right, just a small semantics. Something called explicit and implicit equation. We'll see those particularly with like circles and stuff. An explicit equation is one we deal with almost all the time. That will be an equation that's actually solved for a specific variable. So an equation solved for a specific variable. An equation solved for a specific variable. An example of that might be y equals plus or minus the square root of x plus 4. Anything. That's just an example. All right, I'm not picking specific ones. It's just solved for y. Guess what an implicit one is? That's not solved for a specific equation. So yeah, an implicit is going to be an equation not solved for a specific. An equation not solved for a specific variable. I think a good one to do here would probably be a circle, which would be something like x squared plus y squared equals 4. Because circles a lot of times aren't written explicitly. A lot of times they're just written implicitly. Because an implicit of this, that would have an origin of 0, 0 and would have a radius of 2. You actually get more information from your implicit formula of a circle than you would from your explicit formula. All right, next one says write each equation explicitly in terms of x. Now, I only put these really on there for you to understand the terminology here. Doesn't that almost look like it says solve for x? That's not what it means. When I say write an equation explicitly in terms of x, that actually means solve for the other variable, that x is the thing that's our input. This is telling you write an equation where x is your input. So that means we need to solve for y. So solving for y, we'll have a negative 4y equals a negative x plus 20. Then we should divide everything by a negative 4. That means we divide everything by a negative 4. People often forget that. That will leave me with y equals, I'm going to turn that into 1/4 x minus 5. Oh. What was that?
Plus 5.
No, because we're dividing by a negative 4. So switch the sign. That's why I put a negative on. I put a negative on every one of those to remind myself. All right, like I said, the most time you see an implicit equation is for circles, but you can't plug an implicit formula in your calculator. So if I needed you to graph this in a calculator, you'd first have to solve for y. So that means we would just go ahead and move the x to the other side. So I would have y squared equals a negative x squared plus 25. Then we'll take the square root of both sides, give me y equals plus or minus the square root of negative x squared plus 25. That is fully simplified. Square roots do not break apart when there's a plus or minus underneath it. Only if there's a multiplication. You cannot break that apart any further. This is done. So you can't rewrite that as square root of negative x squared space plus space square root of 25. So you can't take the square root of anything there. This is as simplified as you can do it. Do not break it apart. The only time you can break it apart if it's multiplication. All right, the very last thing we're going to cover is function notation. Function notation, which equation did I use here? Did I not even do it? I didn't even do it. So we'll pick an equation. We'll go y equals 3x squared plus 5. All function notation does is it replaces your output with f of your input. F of your input. So if I need to write this in function notation, I'd go f of x equals 3x squared plus 5. Here's some good things about function notation. If I wrote something in function notation, it automatically is a function. You can't write in function notation unless it's a function, i.e. function notation. Function notation also gives you what your input needs to be. Your input needs to be x along the way. There's never a question of what your input or output is. So this says, hey, you got a function and you got an input. This also lets you name functions. So look at that f there. That f really just stands for a name. I could call it g of x. I could call it h of x. So what I'll do a lot of times on quizzes and tests, I'll give you a bunch of different ones. I'll say this is g of x, this is f of x, this is h of x. Find h of 3. You have to figure out what equation I'm talking about and what number to plug in for your input. So these are pretty standard, but if I look at find f of negative 5, perhaps I have to find out what function name is f. Well, that's the one right next to it. So nothing crazy there. So we'll just do f of negative 5 means plug in negative 5 for all of my inputs. So I'm going to have negative 5 squared minus 6 times a negative 5 plus 23. I highly encourage you to use parentheses every time you input, because you're going to be dealing with negatives. You'll also be dealing with ones that I might ask you to do f of x plus 1, where you have to replace all your x's with x plus 1. No matter what's here, you need to replace your x with it. If I put smiley faces here, you have to replace all your x's with smiley faces. This says, Simon says, plug a negative 5 in there, so you have to replace them all with negative 5s. No matter what I put in there, you have to replace it with what's there. Now let's go ahead and simplify. Turns out negative 5 times negative 5 is not negative 25, as some of us thought on the test. It would be a positive 25. We'll have a negative 6 minus or times a negative 5, which will turn into a plus 30, plus 23. All right, that's going to give us what? 55 plus 23 is going to be 78. Did I even have that one on here? All right, like I said, I might not use F's. They might be H's. If I say find h of 9, you first have to find the equation h. Well, just happens to be right next to it. That won't always happen. But that means find h, which is right here, and plug 9 in for there. So we'll have h of 9 is going to equal 7 minus 9 squared. Will that make it 7 plus 81? No. That's why I put parentheses there. So you don't accidentally do negative. This is saying do regular 9 squared, which is 81, and then attach the 7 minus. So we'll have 7 minus that 81, which is going to equal a negative 74.